Suppose we want to choose 6 colors without replacement from 13 distinct colors. How many ways can this be done if the order of the choices is not relevant? So what does that mean, not relevant? That means order does not matter. And if order does not matter, you're counting in a way that resembles combinations. As soon as you combine them, you're done. So you don't have to count another ordering of the same combination. Why don't we do example A first? We actually have a formula for that, and we read that as n choose r, and that is n factorial over n minus r in parentheses, then factorial, times r factorial. So n choose r. In our case, we actually know our n. Our n is 13. We have a sample of 13. And we want to choose 6 of them at a time and make a combination out of them. So how many possibilities are there? Well, I'm sure you could take it from here. You just want to simplify this expression, 13 factorial over parentheses 13 minus 6 factorial times it by 6 factorial, which is 13 times 12 times 11 times 10 times 9 times 8 times 7 factorial, all over 7 factorial. Now, 6 factorial, I'm going to write 6, and then I'm going to write times 5 factorial, but 5 factorial is 120. Remember that, that's a very popular number. 5 factorial is 120, so now we could start reducing a common factor of 120. Those are gone. We could reduce a common factor of 7 factorial. That is gone. And 6, there is a 2 there, and then there's a 3 as well. So we could reduce this even more. What would this reduce to? Let's find out. That's 13 is a prime number. 11 is a prime number. We're going to reduce a 3 from the 9, so we're left with a 3. We're also going to reduce a 2 from the 8, which means we're left with a 4. And that's it. The denominator is now 1, and so we just need to do that. You could use a calculator there. That's 13 times 12 times 11. And we get 1,716 combinations. How about part B? Part B says the order of the choices is relevant. So if you pick red first, you mean, oh, the color red must be first, right? And then if you pick red second, that is actually a different ordering. So here we say order does matter, or order matters, and then you want to think of permutations. Permutations include all the orders. So it includes possibilities and include the ordering of those possibilities. And we have a formula for that as well. We say n permute r. Out of a sample size of n, we're going to permute r of them at a time. That is n factorial all over parentheses n minus r factorial. We now need to find this expression. Remember, n is 13. We're trying to find 13 and then permute 6 of them at a time. And using this formula, we have 13 factorial over 13 minus 6 factorial, which is 7 factorial. And that is, of course, 13 times 12 times 11 times 10 times 9 times 8. And go ahead and use a calculator to get that. The calculator says 1, 2, 3, 5, 5, 2, 0. Wow, that's 1,235,000 520 orderings or permutations. So let's label that as number of permutations there. Boop.